Electricity. The key areas covered will be AC and DC electricity supplies, frequency and voltage equations for AC supplies, and oscilloscope traces. What we will do today is revise the definitions of AC and DC electricity supplies, state UK mains frequency and voltage, carry out calculations on AC supplies, and use oscilloscope traces to determine values for use in the above calculations. Here is some background revision on AC and DC. There are two types of electrical current. Direct current, DC, where the electron flow is in one direction, for example, a battery. And alternating current, AC, where the electron flow is constantly changing direction, for example, the mains socket. An alternating current is produced by an alternating voltage. We can see our voltage time graph here, and also a current time graph, and here is one cycle. Here is some background revision on oscilloscopes. An electronic device called an oscilloscope can be used to draw a graph of the electrical signal of both AC and DC. Here is a graph of AC. We can see that the signal is above and below the x-axis. Here is an example of DC. The signal is above or below the x-axis. Using an oscilloscope. Oscilloscopes have dials on them to allow you to calibrate two things about the signal produced. On the x-axis, the time per centimetre, so that's the time base often given in milliseconds. And on the y-axis, volts per centimetre. The voltage gain is often given in millivolts. Frequency. Frequency, F, is the number of complete cycles per second of the alternating current and is measured in hertz. The period, T, is the time taken for one complete wave to pass a point, so one complete cycle, and is measured in seconds. Here is the equation that we use to relate the two. F equals 1 over T. The frequency of UK main supply is 50 Hz, so the current goes to and fro 50 times a second. Measurement of frequency using an oscilloscope. An oscilloscope can be used to find the frequency of an AC supply. For example, the time base setting on this oscilloscope is set to 0.005 seconds per centimetre. This means that the dot on the oscilloscope takes 0.005 seconds to travel each centimetre to the right across the screen. Each cycle, so one wave, is complete in 4 centimetres, so the total time for one cycle is 0.005 times by 4, which is 0.02 seconds. This time is called the period. Remembering back to our equation, F equals 1 over T, we can put this 0.02 into our equation and come out with our frequency of 50 Hz. Example 2. Calculate the frequency of the supply. First of all, we want to write down the equation that we need to use. So frequency equals 1 over the period of the wave, but we need to figure out the period of the wave first. If we start looking at our wave just here, we can see we need to go 1, 2, 3, 4, 5, 6 divisions before we get to the start of the next wave. So one cycle is 6 divisions. The period of the wave is 6 because 6 divisions times by the time base, and we can see that is 10 milliseconds per division. So 6 times 10 milliseconds is equal to 60 milliseconds. We can now put this into our equation. So the frequency equals 1 over our 60, and don't forget about the milli, so that's times 10 to the minus 3, and that is equal to 16.6 recurring, and we can round that to 17 Hz. Example 3. Calculate the frequency of the supply. So we're going for the same method as before. So we've got our frequency equals 1 over the period of the wave. And on our oscilloscope screen, we can see if we start off here, we have to go 1, 2, 3, 4 boxes this time to get to the start of the second wave. So one cycle is 4 divisions. Therefore, the period of the wave is our 4 divisions times by the time base of 20 milliseconds, which is equal to 80 milliseconds. So our frequency is going to be 1 over 80 times 10 to the negative 3, which is equal to 12.5 Hz. Example 4. An AC source of 50 Hz is connected to a CRO, which is a cathode ray oscilloscope, and the following trace obtained. Find the time base setting on the CRO. So first of all, we can write down our equation. We've got F equals 1 over T. We can also write this as T equals 1 over F. We can then work out the period of the wave. T equals 1 over 50, that was given in the question, and that equals 0.02 seconds. Looking on our oscilloscope, we can see that starting at the start of the wave here, we've got 1, 2, 3, 4, 5, 6, 7, 8 divisions to get to the start of the next wave. So one cycle is 8 divisions. If one cycle is 8 divisions, we can work out our time base by dividing 0.02, so our period, by 8, which is 2.5 milliseconds, and that's per division. Example 5. An alternating voltage produces a trace on an oscilloscope screen as shown in figure 1. The time base setting of the oscilloscope is 50 milliseconds per centimeter. A. How should the time base setting be changed to obtain the trace as shown on figure 2? B. Draw what would be obtained on the screen if the time base was now switched off. Let's try part A first. We can see on our first diagram that there are 3 divisions per one wave. You can see here, start of the wave, 1, 2, 3, we have 3 divisions per wave. For the second one, we have 1, 2, 3, 4, 5, 6 divisions per wave. So what we need to do is take that oscilloscope setting of 50 milliseconds per centimeter and half it to 25 milliseconds per centimeter. So from 50 milliseconds per centimeter, the first one, we do 50 times 3, that's 150 milliseconds as the period for the wave. And we're just doing this to make sure, you don't have to do this in the actual question, we're just showing that our period is still the same for both. For the second one, we've got 25 milliseconds per centimeter. Our period will be 6 this time, times our 25, and that again is equal to 150 milliseconds. So we can see these waves are still equal in their period, but our time base is different. For part B, we need to draw what would be obtained on the screen if we turn the time base off completely. Here we have our oscilloscope screen, and if we think about the time base being switched off, we will have no right to left movement, but we will still have vertical movement. So our line just looks like a vertical line, still reaching the peak and trough that it did in our initial example where the time base was switched on. Voltage. When we consider voltage, there are 2 values that we must consider: peak voltage and the RMS voltage, that's the root mean square voltage. Note, when an athlete is at their peak, we say that they are at the absolute best. Will an athlete be at their peak in every performance? No, they will not. Therefore, the peak is the absolute maximum, i.e. the peak voltage is always larger than the RMS voltage. Root mean square voltage, that's the RMS voltage. The current and potential difference of an AC supply vary continuously, and so the effective value of these quantities is less than the maximum value. The maximum value is called the peak value. The effective or quoted value is less than the peak. We can see this on the graph there. Our peak value is up at the top and also at the bottom because our peaks and troughs reach the same level. And our RMS value is less than that peak, and that is what is quoted. From the graph, it's obvious that the peak value would not be a very accurate measure of the voltage available from an alternating supply. In practice, the value quoted is the root mean square voltage. The root mean square voltage of an AC supply is the value, the DC voltage, which will give the same dissipation of power, which is heating effect, in a fixed resistor as the AC voltage. For a sinusoidal voltage or current, Vrms equals Vp over root 2, and Irms equals Ip over root 2. The UK mains RMS voltage is 230 volts. This means that our peak voltage is actually up about 320 volts. Example 1. An AC voltage is applied across the input of an oscilloscope and the following trace is seen. The grid lines are 1 cm apart. If the Y gain control of the oscilloscope is set at 10 volts per centimeter, calculate the RMS voltage. First of all, we can say that our peak voltage is actually the amplitude here. And if our peak is at 4 divisions high and it's 10 volts per division, we can say that's 10 times 4, which is 40 centimeters, not centimeters, 40 volts. Now we can use our equation. VRMS equals VP over root 2. So our RMS voltage equals 40 over root 2, which is equal to 28.28 and so on. We can round this to 28 volts. Example 2. A signal generator output is measured at 5 volts, and that's our RMS voltage. What is the peak voltage? Again, we need to use our equation for this. So we have VRMS equals VP over root 2. We now want to substitute in our values, so we've got 5 equals VP over root 2. Rearranging this, we get our peak voltage equals 5 multiplied by root 2, and this gives us an answer of 7.071 and so on, and we can round this to 7 volts. Example 3. An electrical heater rated at 25 watts is connected to an AC source where the peak current is 0.8 amps. What value of DC would be needed to give the same power output from the heater? We know that the current in DC is the same as the RMS current in AC. And this is equal to our peak current divided by root 2. We can substitute our values here, so we have 0.8 over root 2. This gives us 0.565 and so on, and we can round this to 0.6 amps. Example 4. The peak value of an AC in a 3 ohm lamp is 4 amps. Calculate the average power output of the lamp. First of all, let's use our equation for the RMS current equaling the peak current over root 2. We've got 4 over root 2, which is equal to 2.82. Let's round this. In fact, 2.828. We can round this to 2.83. We're rounding to 2 decimal places because we need to then use this value in another equation. To calculate the power, we've got P equals I squared R. Putting our I in there, 2.83 squared, times it by our resistance, which is 3, we get an answer of 24 watts. If we had rounded the 2.83 up to maybe 3, like we were doing before for our values, this would not have given us a more accurate result. So we need to, in the intermediate stages, round to more decimal places to give us a much more accurate result. Experimental comparison of the peak voltage and the RMS voltage. A light bulb is a convenient indicator of the power delivery of a voltage. We can see in our diagram here, we've got an AC supply and a DC supply. We've got a light meter, a switch, a variable resistor, a CRO, remember that means cathode ray oscilloscope, and this measures the voltage across the bulb. The light meter measures the output of the bulb, first from an AC supply and then from a DC supply. The variable resistor is adjusted until the lamp is equally bright from both sources. The peak voltage of the AC supply and the equivalent steady voltage of the DC supply can be measured by the cathode ray oscilloscope. When the bulb is equally bright from both sources, we should find that our peak voltage equals root 2 times our voltage in DC. But our voltage in DC is equal to our RMS voltage. Therefore, our peak voltage is equal to root 2 times our RMS voltage. Let's try some past paper questions. The output from a signal generator is connected to the input terminals of an oscilloscope. The trace observed on the oscilloscope screen, the Y gain setting, and the time base setting are shown in the diagram. The frequency of the signal shown is calculated using the A. Y gain setting and the vertical height of the trace, B. The Y gain setting and the horizontal distance between the peaks of the trace, C. The Y gain setting and the time base setting, D. The time base setting and the vertical height of the trace, or E. The time base setting and the horizontal distance between the peaks of the trace. This question is asked specifically about the frequency, and we know that we can calculate the frequency using F equals 1 over T. We calculate the period, which is T, using our number of divisions across the x-axis and we use our time base setting for this because the period is the time taken for one wave to pass a point. So looking at our options, we know that we're ignoring the Y gain because that's to do with the voltage. Part D has the time base there, but it's talking about the vertical height of the trace, so we know that's wrong. Looking at E, we've got the time base setting and the horizontal distance between the peaks of the trace. That horizontal distance works with this x-axis divisions, so we know our answer is E. An AC signal is displayed on an oscilloscope screen. The Y gain and time base controls are set as shown. What is the frequency of the signal? So again, we need to use F equals 1 over T, but first we need to work out our period. So looking at our oscilloscope screen, we can see that there are 4 divisions for one complete wave. We can start here, go 1, 2, 3, 4, that's one complete wave. So 4 times by 0.5 milliseconds per division. So 4 times 0.5, we have 2 milliseconds. Putting that into our equation, we've got F equals 1 over 2 times 10 to the negative 3, which is equal to 500 Hertz. We can see this is an answer up here, it is answer E. A signal from a power supply is displayed on an oscilloscope. The trace of the oscilloscope is shown. The time base is set at 0.01 seconds per division and the Y gain is set at 4 volts per division. Which row in the table shows the RMS voltage and the frequency of the signal? Let's calculate our RMS voltage first. We know the equation to use is V RMS equals Vp over root 2. We know our peak voltage, we can work it out from the graph. We have 3 divisions to get from the center up to our peak, and it's 4 volts per division. So we know our peak voltage is 4 times 3, which equals 12. Putting this into our equation, we've got 12 over root 2, which is equal to 8.5 volts. So on the table there, we can see that both A and D have 8.5 volts. So now we need to go into our frequency. F equals 1 over T. Our period, we can see on the oscilloscope, we have 1, 2, 3, 4 divisions per wave, and it's 0.01 seconds per division. So 4 times 0.01 is equal to 0.04. So our frequency is equal to 1 over 0.04, and that is equal to 25 Hertz. On our frequency column, we can see A, B, and C are all 25 Hertz, so the only column with both of these values in it is A, and that is our final answer. A signal generator is connected to an oscilloscope. The output of the signal generator is set to a peak voltage of 15 volts. The following diagram shows the trace obtained, the Y gain, and the time base controls on the oscilloscope. The scale for the Y gain has been omitted. 1. Calculate the Y gain setting of the oscilloscope. 2. Calculate the frequency of the signal in Hertz. Let's try question 1 first. To calculate the Y gain, we can have a look at our peak voltage. Our peak voltage is 15 volts, and we can see that there are 3 divisions from the midpoint of our wave to the top. So if we do 15 divided by 3 divisions, this equals 5 volts per division, and that's our Y gain setting. Having a look at question 2, we want to work out the frequency. So using our equation, F equals 1 over T. First of all, we want to work out T. So looking at our graph again, we can see 1, 2, and a half divisions. If you're not sure about how precise this is, go more divisions. We've got 3, 4, and 5 divisions is 2 waves, so it must be 2.5 divisions for 1 wave. So we've got 2.5 divisions times by a time base of 1 millisecond. So we've got 2.5 milliseconds for our period. So our frequency is 1 over 2.5 times 10 to the negative 3, and that is going to be 400 Hertz.